In this video, we're going to look at section 9.5, which looks at the Rao-Blackwell theorem and minimum variance unbiased estimation. Alright, so if the expected value of theta hat equals theta, and u is a sufficient statistic for theta, then there is a function of u that is also unbiased and has variance that is no larger than the variance of theta hat. What this means is that the unbiased estimator, which has the smallest variance, is a function of a sufficient statistic. So if you'll remember, sufficiency, what it does is it tells us that we're not losing any information about the parameter that we're trying to estimate. So what this is essentially doing for us is it's kind of giving us a way that we can find an unbiased estimator that has minimum variance. So to find that unbiased estimator, which has the smallest variance, we can limit our search to sufficient statistics. And so we've already seen how to show that a statistic is sufficient. So this is giving us a way to find these estimators. So we're going to look at what is called the Rao-Blackwell theorem, and it states the following. So we're going to let theta hat be an unbiased estimator for theta such that its variance is finite. So we do need it to have finite variance. Then if u is a sufficient statistic for theta, we're going to let theta hat star be equal to the expected value of theta hat conditional on that sufficient statistic. And what that tells us is that the expected value of theta hat star is going to be equal to theta, and the variance of theta hat star will be less than the variance of theta. So what the Rao-Blackwell theorem is doing for us is it's going to give us a technique which is going to allow us to reduce the variance of our current estimators. Now remember, we could always find, one that reaches the minimum. But this can be difficult for several reasons. So first, it's usually very difficult to find this expected value of theta hat given u. And then second, if you apply this theorem a second time using the same sufficient statistic, so think, we keep on applying this iteratively, so let's say we had a theta hat double star, then you're going to usually end up getting the same estimator back. So to get different unbiased estimator with a smaller variance, you have to use a different sufficient statistic. Because again, remember the sufficient statistic, it's, you can think of it as getting rid of some of that extra information we don't need about the parameter. So in particular, we need to use the sufficient statistic that best summarizes the information in the data about theta. And this sufficient statistic is called the minimal sufficient statistic, or the MSS. And so here's a fact. An unbiased estimator that is a function of the minimal sufficient statistic is a minimum variance unbiased estimator, and we abbreviate these by MVUE. In other words, it's going to have the smallest variance among all unbiased estimators. So this is a good thing. This is what we want. And so the reason this is true has to do with the Rao-Blackwell theorem. However, the argument and the proof of it is fairly complicated, and we're not going to go through it. So to find the statistic, which is the MVUE, what we're going to do is we're first going to learn how to find the minimal sufficient statistic, which is the MSS. And so the text says that the sufficient statistic we get from the factorization criterion that we saw previously is usually an MSS. However, we're going to learn a technique to directly find these. And so this is going to bring us to what is called the Lehmann-Scheffé technique. So the Lehmann-Scheffé technique says the following. Suppose that y1 through yn have this following likelihood function. And we're going to consider 2 points, an x, or a set of x's, and a set of y's. And what we're going to do is we're going to look at the ratio of the likelihood for the x's and the y's. And what we're going to do is find a function g such that that ratio is free of theta if and only if g of the x's and g's of the y's are equal to one another. If we can find such a function, then u, which is going to be equal to that function, is going to be a minimal sufficient statistic for theta. So we're going to look at some examples of this. So our first one says, let x1 through xn be IID binomial 1p. And so we're going to find a MSS for p. So let's see how we do this. So remember that we've previously already shown what the likelihood is. So let me put that down. And I'm going to write the likelihood here in terms of y's, but that doesn't really matter. So we've got our likelihood function here. So we have p to the sum of the yi and 1 minus p to the n minus the sum of the yi. So next what we're going to do is we're going to set up this ratio. And what we're going to do in the numerator is we're going to have the likelihood function in terms of x's. And in the denominator, we're going to have the likelihood function in the terms of the y's. So just writing down what r is equal to. And next what I'm going to do is substitute in the likelihood, again in the numerator using x's, and the denominator using y's. So again, in the numerator, we've got the likelihood in terms of x's, and in the denominator, the likelihood in terms of y. So we can simplify this. So first, for the p's, notice we're going to have the sum from I equals 1 to n xi minus the sum I equals 1 to n yi. So that's coming from looking at these two terms right here. Next, we have 1 minus p, and we're going to have 1 minus p to the n minus the sum I equals 1 to n xi minus n minus the sum I equals 1 to n yi. Notice we've got some cancellation here. The n's are going to cancel. So let's go ahead and write that out. And now notice both of the exponents here are in terms of the sum of the xi and the sum of the yi, so we can write this as the following. We could have p divided by 1 minus p times the sum of the xi minus the sum of the yi. And notice that's true because here these signs are the negative of these signs, so that's why we have 1 minus p in the denominator here. So this is what r is equal to, and our goal is we're trying to find a g such that R is free of theta if and only if G of the x's is equal to G of the y's. So notice in this case, R is free of P, if and only if the sum from I equals 1 to n xi minus the sum I equals 1 to n yi. So in other words, since this is in the exponent, the only way for this entire thing to be free of P is if this would be equal to 0, and then the whole thing becomes 1 and P is no longer here. So what we're going to do is we are going to let U be equal to the sum I equals 1 to n yi. And again, it's because that sum is our G. So we're going to let U be equal to G applied to the random variables. So by the Lehmann-Scheffé technique, U, which is equal to the sum I equals 1 to n yi, is a minimal sufficient statistic for P. Now, the reason that we're doing this is because this is going to help us find that minimal variance unbiased estimator for P. That's kind of our whole goal here. So let's do that in the next part. So to find that MVUE for P, what we do is we need to find a function of the MSS. And we want that function to be an unbiased estimator for P. Well, notice that if we take the expected value of the U that we just found, in other words, the sum of the yi, well, that's equal to the expected value of the sum I equals 1 to n yi, which is equal to the sum I equals 1 to n, the expected value of y. And remember that we're working with a binomial here, so this is going to be equal to NP. So what we could do is we could use P hat, which would be equal to U divided by N. So notice this is a function of the MSS, which is equal to the sum I equals 1 to n yi divided by n. Or in other words, that is the sample proportion that we have seen before. So P hat is the MVUE for P, since it is a function of a MSS. And it is an unbiased estimator of P. All right, moving on. We're going to look at some more examples here. All right, this one says, give me just a moment, I lost my page here. Here we go. We're going to let y1 through yn be IID with a Rayleigh distribution defined on page 318 of your text. It's a special case of a Weibull distribution, which is another distribution. You don't hear about that often, but it is used in practice a lot. So here's our distribution. So we're going to do the same thing that we just did. Now, previously, we already looked at the likelihood for this function, so I'm going to go ahead and write that down. Sorry, I'm kind of running out of room here. Alright, so the first thing we're going to do is we're going to set up that ratio just like we did before. So our ratio, we're going to start out by looking at the ratio of the likelihood in the numerator for x and in the denominator for y. Okay. And then again, I'm going to write out the likelihood for x and for y for this particular distribution. Alright, and now we can simplify this. We get the product from I equals 1 to n xi over the product I equals 1 to n yi times e to the negative 1 over theta times the sum of the xi squared minus the sum I equals 1 to n yi squared. All right. So next, notice that r is free of theta if and only if the sum I equals 1 to n xi squared minus the sum I equals 1 to n yi squared is equal to 0, so that e to the 0 is equal to 1. And notice we're not concerned with this piece here, because if these two become 0, then the whole thing is free of theta. So by the Lyman-Shaffer theorem, or Lyman-Shaffer technique, I should say, U, which is equal to the sum I equals 1 to n yi, is a MSS for theta. All right, so now we can use this to find the MVUE. So as a reminder, what we're doing is we need a function of the MSS that is an unbiased estimator of theta. Okay. So what we're going to do is we're going to start out by looking at the expected value of u. If u is biased, then we're going to try to find some function of u that is unbiased. So we're going to start out with our expected value of u. So notice that that is equal to the expected value of the sum from I equals 1 to n yi squared, which is equal to the sum I equals 1 to n, the expected value of yi squared. Now we need to find the expected value of y squared for this distribution, so that's what we're going to do next. So the expected value of y squared, we're going to integrate from 0 to infinity y squared 2y over theta e to the negative y squared over theta dy. To do this, we're going to let w be equal to y squared. And notice if we do this, that dw is equal to 2y dy. And in this case, we now have the expected value of y squared is equal to the integral from 0 to infinity 1 over theta w e to the negative w over theta dy, which is equal to the expected value of w, where w is exponential. And I just realized I believe I should have dw here. So what that tells us is we don't actually have to integrate this, because the expected value of y squared is equal to the expected value of w, where w is distributed exponential. So this is just equal to theta. And what that tells us is that the expected value of u is equal to, again, the sum I equals 1 to n, the expected value of yi squared is going to be equal to n theta. So u is biased, but it's really easy to make u an unbiased estimator. So what we do is we take u divided by n, which again, that's going to be equal to the sum of the yi squared divided by n, and it is going to be an unbiased estimator of theta. And then since it is also a function of the MSS, the sum I equals 1 to n yi squared divided by n is a MVUE for theta. have another example. This one says, suppose that y1 through yn are IID normal mu sigma squared. We're going to find MVUEs for both sigma and theta. All right, so notice that f of y given mu sigma is equal to 1 over sigma times the square root of 2 pi e to the negative 1 over 2 sigma squared y minus mu squared. So therefore we need to get the likelihood function. So the likelihood function is going to be equal to y1 through yn, and you could have had x's here, given mu, and I should have had a given sigma squared there, given sigma squared is equal to 1 over sigma times the square root of 2 pi e to the negative 1 over 2 sigma squared y1 minus mu squared all the way out to 1 over sigma times the square root of 2 pi e to the negative 1 over 2 sigma squared yn minus mu squared. So we can combine terms here. And this is going to become 1 over sigma times the square root of 2 pi to the n, because there's going to be n of these terms, times e. All of the e's are going to have 1 over 2 sigma squared. And then each of them is going to have a yi minus mu squared. So this is going to be equal to the sum, I equals 1 to n, yi minus mu squared. All right, now that we have this piece, we can look at that ratio. So again, setting up our ratio is going to be equal to the likelihood evaluated at the x's, given our two parameters of interest, divided by the likelihood evaluated at the y's, given our two parameters of interest, filling in what each of those likelihoods are. We've got 1 over sigma, 2 times the square root of pi to the n, e to the negative 1 over 2 sigma squared times the sum, I equals 1 to n, xi minus mu squared, 1 over sigma times the square root of 2 pi to the n, e to the negative 1 over 2 sigma squared times the sum, I equals 1 to n, yi minus mu squared. All right, so we can see right off the bat that these two terms are going to cancel. And so this is going to leave us with e to the negative 1 over 2 sigma squared times the sum, I equals 1 to n, xi minus mu squared minus the sum, I equals 1 to n, yi minus mu squared. All right, so let's work with this piece here just a little bit. So note the following. We've got the sum, I equals 1 to n, xi minus mu squared is equal to, well, we're going to expand this out. If you saw a sudden jump in the video, I apologize. I had a little bit of technical difficulty and had to splice two videos together. So here we are. We were looking at this note here. We were looking at the sum, I equals 1 to n xi minus mu squared. and we were noting that this is equal to the sum I equals 1 to n xi squared minus 2 mu times the sum I equals 1 to n xi plus n mu squared. And notice we could do the same thing for the y's. So what this tells us, if we recall what r was equal to up here, is that r is going to be equal to e to the negative 1 over 2 sigma squared times the sum I equals 1 to n xi squared minus the sum I equals 1 to n yi squared minus 2 mu times the sum I equals 1 to n xi minus the sum I equals 1 to n yi. Notice we had some terms that canceled out, like the n mu squared and the n mu squared here. So notice r is going to be free of mu and sigma squared. So here's our mu and here's our sigma squared, if and only if this piece and this piece are equal to 0. So therefore, we can apply the Lehmann-Scheffé technique. So by the Lehmann-Scheffé technique, our minimal sufficient statistic is actually going to be two values. It's going to be a vector. So it's going to be the sum I equals 1 to n yi squared, comma, the sum I equals 1 to n yi. And so these are going to be the minimal sufficient statistics for mu and sigma squared. Now, remember, our goal is to find the minimal variance unbiased estimator. We could consider the following. And we've previously shown that both of these are unbiased estimators. And then since the y bar and the s squared are both functions of the MSS, y bar and s squared are MVUEs of mu and sigma squared. All right, on the next page. So this page says, suppose that y1 through yn are iid exponential theta, find the MVUE of the variance of yi. All right, so this problem right here, this is actually going to be your quiz problem. So this is going to be your quiz for section 9.5. And I'm going to give you a couple hints for this. Now notice we're trying to find the variance of yi. So notice this is the same thing. Since this is an exponential distribution, you're trying to find the MVUE of theta squared. So the first thing that you're going to want to do is you're going to want to do the exact same thing that we've been doing, and you want to find the MSS first. So that's going to be your first step. 2, after you find the MSS, you're going to use the MSS to find the MVUE for theta. And so 1 and 2 are going to be just like the examples that we saw. And what you should find is that the MVUE for theta is y bar. Okay. Next, remembering that your goal is to find the MVUE for theta squared, what you're going to do next is you're going to try to see if y bar squared is unbiased for theta squared. And what you're going to find is it is not unbiased. It is going to be a biased estimator. And so you're going to work with that estimate. And then for what you should find as your MVUE of theta squared is n over n plus 1 of y bar squared. So that's kind of the steps that you're going to want to follow for this problem. And then there's going to be more information on Blackboard as far as, how to submit the quiz. All right, and then we just have one more page here. So we have this note, and it says, if we use the MVUE of theta to find a confidence interval for theta, we usually get the shortest possible confidence interval. And this makes sense because if we're finding the estimator that is unbiased and it has minimal variance, remember that part of the formula for a confidence interval takes into account that variance of the estimator. So if it has the smallest variance, it's typically going to get the shortest possible confidence interval. So kind of a summary of this section is we first find the we try to find the MVUE, and to do that, we first find the MSS. And then we modify the MSS so it's unbiased because we want a function of that minimal sufficient statistic. And the result of that is going to be the MVUE by Lehmann-Schiffer. Now, just a note here, sometimes it's very hard to modify the MSS so it's unbiased. And so you can use the Rao-Blackwell theorem to help. So this concludes the section 9.5 notes.